150 million kilometers away from Earth, an outburst occurs on the surface of the Sun. In just a few seconds, it sends out a seething cloud of charged particles and super hot gases. This massive space weather front travels on the solar wind, a stream of material that constantly blows away from the Sun. When the storm front arrives at Earth, it energizes electrons and ions in our upper atmosphere. Out in the countryside near Boston, Massachusetts, scientists at MIT's Haystack Observatory study the geomagnetic storms triggered by solar outbursts. They're working to understand the effects on Earth's upper atmosphere when the Sun stirs up a little space weather. Our planet's atmosphere is a blanket of air that is thick near the surface and gets thinner the higher up you go. We live and travel through the troposphere, the lowest part. Next is the stratosphere, which contains the ozone layer and high, thin clouds. The mesosphere is where we see incoming meteors burn up. Above that is the ionosphere, an electrified region where space weather has its greatest effect. Haystack researchers analyze how the ionosphere is affected by the solar wind. They also measure how it interacts with the magnetosphere, the region of space around Earth that is influenced by our magnetic field. The Sun is the source of all the space weather that buffets the ionosphere and magnetosphere. Like every other star in the universe, it is an active, seething sphere of hot gas. When a cloud of gas and charged particles, called a plasma, escapes from the Sun, we find out about it pretty quickly. The light from the outburst reaches our planet in about 8.5 minutes. The plasma takes longer. It usually arrives within 2 to 3 days and collides with our magnetic field. That action sparks huge electrical storms high in the ionosphere and creates blazing displays of northern and southern lights. Space weather can have more serious consequences. In March 1989, a series of solar disturbances triggered violent geomagnetic storms. They knocked out the power for more than 6 million people across eastern Canada. For that reason, researchers want to understand space weather and how it can affect people and technology here on Earth. Dr. Philip Erickson is part of Haystack's team of space weather researchers. They use the Millstone Hill radar antennas to study the ionosphere.
Right now, these big antennas behind me are tracking changes in Earth's ionosphere. They're telescopes, but they use radio waves instead of visible light. We use the radar signals from these instruments to track the temperature and chemical composition of the gases in Earth's ionosphere. We also use our radar data to learn more about the ions and electrons in the atmosphere, how hot they are, how many there are, and how fast they are. We also measure the effects of the solar wind as it slams into the ionosphere. Our instruments are very accurate and can measure the ionosphere all along the eastern United States. We take the data our radar provides and get an idea of the physical state of the ionosphere. We can use this information to track changes in the ionosphere and relate it to changes in the solar wind and other space weather events. These days, we've added a new instrument to our ionospheric study toolkit, GPS.
Global Positioning System satellites continually relay radio signals to ground receivers. Those signals contain timing information and data about the satellite's locations. That information is then analyzed and turned into other data that can be used by airplanes and boats for navigation. Automobile GPS systems also use the same information to help drivers find their destinations. Banks and financial institutions depend on precise GPS signals to help them transfer money on time. And every cellular telephone network relies on GPS timing data. So, how can space weather affect all of these systems? Solar storm fronts rapidly push clouds of ions and electrons into small regions of the ionosphere. This interferes with broadcast signals from communication satellites and radio signals from the GPS satellite network. Solar storms can also stir up strong electrical currents that could overload power grids and shut off the lights for millions of people. If communication networks and power companies have enough advance warning, they can take steps to protect their systems until the storm is over. During such solar storms, ships and airplanes can switch to other navigation methods until reliable GPS signals are available.
Today at Haystack Observatory, we're using GPS data collected during solar storms to better understand how space weather changes our ionosphere. What we learned by analyzing the data together from our radar antennas and GPS units is of immense importance. Space weather isn't just out there. It affects us right here on Earth.